Stand on the East Antarctic Plateau, and you are surrounded by extreme altitude and severe hypoxia. The air is so cold that your exhaled breath instantly shatters into a crystallized ice fog. Without heavily insulated gear, taking a single deep breath of this super-cooled, dry air will literally freeze the tissue in your throat and lungs. The ultimate test of human endurance in this environment occurred in April 1982 at Russia's Vostok station. A catastrophic fire wiped out the primary power plant, plunging 13 men into the total darkness of the polar winter. To survive the next 8 months, they had to improvise heaters, burning diesel fuel with scraps of asbestos used as wicks. Living at these extremes relies entirely on machines. When that mechanical life support fails, the environment immediately becomes a lethal trap. For decades, Vostok held the record for the lowest temperature ever measured, hitting -89.2 degrees Celsius. But modern sensors have revealed that the plateau actually gets significantly colder. This thermal map uses data from satellites like MODIS and Landsat 8. It highlights scattered pockets along the high ice divide where surface temperatures plummet to -98.6 degrees Celsius. Dropping to that specific number requires a precise sequence of macro-atmospheric conditions and microscopic terrain features to align perfectly. The East Antarctic Plateau operates as a highly efficient planetary-scale engine, aggressively radiating heat away from the surface. This energy balance visualization shows how the region loses heat. During the months-long polar night, there is zero incoming solar radiation. When the sun does rise, the highly reflective white snow, its albedo, bounces 90% of that light directly back into the sky. Because the surface radiates its energy outward so efficiently, the physical snow skin cools much faster than the air immediately above it, generating a severe temperature inversion. Down on the ground, persistent dry winds carve the snow into sharp, hardened dunes, known as sastrugi. But the absolute lowest temperatures don't occur on those exposed ridges. They happen in shallow topographical swales, tiny dips in the ice that are only 2 to 4 meters deep. As the surface cools, the air becomes incredibly dense. It shrinks, physically cracking the ancient ice below, and then flows downhill like a heavy liquid to pool at the bottom of these swales. These shallow microdepressions act as physical funnels. They trap the supercooled air in concentrated pockets, where it remains still and continues to chill. There is one final ingredient required to push these temperatures to the absolute limit: severe atmospheric dehydration. This diagram shows what happens when water vapor is absent. A highly transparent atmospheric window opens, allowing the last remnants of infrared radiation emitted by the snow to pass unimpeded into the vacuum of space. The temperature drops until it reaches -98.6 degrees Celsius. At that exact mark, the faint amount of downwelling radiation from the dry sky perfectly balances the heat leaving the surface. At this point, the surface has physically exhausted its capacity to lose more heat. Under current atmospheric conditions, this is as cold as the Earth can naturally get. So why do international teams of scientists willingly travel to an environment operating at the absolute limits of human endurance? The exact same physics that make the plateau lethal, the deep freezing and the total absence of moisture, also create the most perfectly preserved climate archive in the solar system. This is the drill camp for the European Beyond Epoca project at Little Dome C. Crews here endure grueling summer averages of -35 degrees Celsius to drill deep into the ice sheet. The logistical hurdle is immense. They are drilling over 3,200 meters down, navigating into highly deformed ancient basal ice layers resting near the continental bedrock. This 2.5D schematic illustrates how they find the right ice. The model tracks the trajectory of ice particles as they slowly flow horizontally and compress vertically toward the bedrock bottleneck over thousands of years. The deadliest surface conditions on Earth act as a hardened roof, sealing in and protecting an invaluable subterranean time capsule. The ultimate prize of this monumental effort is the successful extraction of a continuous ice core dating back more than 1.2 million years. The ancient air bubbles trapped within these pristine cylinders allow researchers to reconstruct atmospheric chemistry through the mid-Pleistocene transition. Decoding these ancient cycles provides the data needed to map how our climate system responds to extreme shifts over geologic time. Enduring these conditions is the price of admission to read our history and to see where the planet is headed next.